welcome to the 11th breakfast seminar. Today we will talk about, me and Omkar will talk about flexibility. I will first present a little bit about our drone factory. We will have another seminar in May about our whole factory, but today I will talk about it regarding the flexibility. And then Omkar will talk about operational flexibility and also how we can increase the flexibility with help of Industry 4.0 technologies and foremost collaborative robot applications. So that's the seminar today. And Omkar will present himself a little bit when it's his turn. My name is Fast-Berglund. I'm a professor at Chalmers University in smart automation, and also I run also the SciLab, Stena Industry Innovation Lab. And what we have done here in the lab, we are building a drone factory, or we have a drone factory. So the first idea with the factory is to demonstrate the technologies and strategies for Industry 4.0. We also want to show different methods for increased digitalization and automation. And we also want to show the whole chain from product design to end customer. Throughout internal logistics, training, final assembly, quality assurance, and so on. So that is the main idea with the drone factory. So we started with Drönare 1.0 in 2018, and our focus were on building a product digitally. To be able to have different types of instructions for operators. So our focus on the first drone was the cognitive automation and instructions for operators. We also focused on two areas, training and final assembly. And we also focused on two methods, design for automated assembly and hierarchical task analysis, or precedence graph for balancing a factory. So that also played a big role on the design of the drone. We designed the drone due to a quite bad design for automated assembly in order to use the DFA2 method in education. We also focused on building a communication from our ERP system, IFS, down to sensor levels. So trying to understand how to change from the traditional automation pyramid down to a more flexible structure with the IoT platform. So in order to increase the product and variant flexibility, we used softwares from PTC in order to build a digital thread of the product. So we have the CAD. We built a digital product in the PLM system. We did a bill of materials, first an e-bill and then a manufacturing bill of material. For the logistics, and then once we had the digital twin of the product, or a digital thread, we could have a flexibility in both the instructions but also in the product variety. So we can present the instructions in many different ways, and we can also change the product quite easily in terms of length of the legs, for example, and other things. So that's the main idea with the digital thread and the digital product, to increase the product and variant flexibility. Another thing that we did regarding flexibility was we wanted to have a resource and route flexibility in our system. So this is a picture of our final assembly. And as you can see here, we have a main conveyor. And then we have these elevators or stations on the main conveyor. We have 6 of these. And the route flexibility is that we can actually change the assembly stations. So they are mobile, we can move them around. So we have these 6 stations, but then we have flexibility to put whatever we want, basically, in terms of stations. So we can have these manual stations, and we can put different resources here in terms of tools and humans and robots. So this was also one of our ideas to build a flexibility in terms of resource and routing flexibility. But we also wanted to have a more automated assembly, so that's why we did some improvements for the drone 2.0. We actually got help from students. Over 200 students did some suggestions in terms of different ideas on how to improve the drone based on the DFA2 method. So some of them was less unique details, more fixtures, integrating different details here, for example, the distances that we used into the frame, and the easier assembly of the legs. So these kind of solutions. So what we did was to create a new drone this year. So this is how the new drone looks like. And the main focus on this type is to be able to produce it or assemble it with many different types of automation. So a flexibility in resource due to physical automation. We also want to focus on more areas. So we are adding internal logistic kitting and quality control. We're focusing on the levels automation method and collaborative robot applications, and also focus on communication, but with this time within different departments system. So a kind of system of system thinking. And regarding the resource flexibility within, we will add collaborative robots. These are the ones that some of the robots that we have in the lab right now. So what we want to do is to add them as resources for the stations. We want to test the different complexity of robots. We want to test the dual arm robots and different interaction between humans and robots. So that will be the next step in the drone factory. Yes, that was what I wanted to present. As I said, we will have more focus on the drone factory on a later breakfast seminar, but this was just a teaser of what we have done so far. And now Omkar will continue to talk about the operational flexibility and how we can actually use these collaborative applications together with other Industry 4.0 technologies. So I will hand over to Omkar.
Thank you, Åsa, for this introduction. Let's begin. My name is Omkar. I'm a PhD student at Production Systems at Chalmers University of Technology, and I'm also a researcher at the Scilab. Many of you are aware of. Today, I'm going to talk about operational flexibility using Industry 4.0 enabling technologies. and a little bit focused on collaborative applications. Yes, also I gave you some introduction about different types of flexibilities and how we use them in the lab. What I look into is the entire systems perspective. So I don't look individually into each flexibility, but I incorporate all of them into one main flexibility. That's what I call, or that's what research says, is operational flexibility. And having a focus on operational flexibility gives system-wide perspective. And yeah, I will talk about it now. But before we talk about flexibility, I want to tell you why we need flexibility. And many of you are aware of uncertainties that we have. We have various types of uncertainties caused by various reasons. The recent one being the pandemic, and it is still causing uncertainties. Last week, I heard on the news that the war trucks has stopped their production because of the lack of semiconductor chips or some sort of chips. So that these types of uncertainties that cause us to halt productions, halt operations on the final assembly line. To overcome these uncertainties, we need flexibility. Having the optimal level of flexibility gives us the opportunity to overcome different types of uncertainties. And a way you can achieve flexibility in many different ways. Manager decisions play an important role. You can optimize systems in different ways. What I look into is using technology. Why technology? You might be aware of these terms, flexible manufacturing systems and reconfigurable manufacturing systems. These have the same core characteristics as operational flexibility, but and they have been around since 2 or 3 decades now. A major limitation or major hindrance for fully to recognize the full potential of these concepts was the lack of proper technology. We didn't have proper technology that can help us achieve highly flexible and highly reconfigurable manufacturing systems before. But today, with the emergence of Industry 4.0 enabling technologies and different types of innovations that come together with Industry 4.0, we can achieve this flexible and reconfigurable manufacturing systems. Now, coming back to operational flexibility, what is operational flexibility? So having operational flexibility means you can use alternate machines to produce your given set of parts. It also means using alternate resources to produce your given set of parts and products. From having alternate machines and resources, operational flexibility also means that you can use alternate resources to alternate processes to produce your given set of parts. So if you have a system where you can easily change your products, your machines, your resources, and even your processes, then you have a good level of operational flexibility. In my research, I have identified 5 different areas for influencing operational flexibility. I will not go deep into each of these areas, but just to give you an indication of what I mean by all this is, when I talk about production systems infrastructure, I talk about the design and the layout of the systems. For machines and equipment, it's the different types of machines and tools and equipments that are used in final assembly systems. Operator training and skills is self-explanatory. Assembly instructions, what I mean by that is what kind of instructions are provided to the operators, how are they provided to the operators. And materials and logistics is how quickly and in the correct manner can a system deliver a given set of material to the correct workstation as fast as possible. So all these different areas play a huge role in achieving operational flexibility, and that's why I've identified them as the key sources of operational flexibility in final assembly. Talking about the enabling technologies, I've identified 7 different Industry 4.0 enabling technologies in final assembly that can be used to enhance the sources that I mentioned before. So 5 different sources can be influenced using 7 different Industry 4.0 enabling technologies. Let's look into some of them. To enhance the training and skills of operators, as well as delivering instructions to operators and at different assembly stations. Sorry, let me rephrase this. We need a highly trained operator, or operator that has different skills to use new technologies in final assembly. A well-trained and a highly skilled operator is capable of quickly adapting to changes in assembly processes. So that increases your flexibility for using that operator into different workstations. To use new technologies and techniques, the operator needs to have enough skills to use them. And also, you need to support operators with different equipments so that you can achieve an optimal level of flexibility. And this can be done using extended reality and Internet of Things. So we can use extended reality technologies such as AR and VR to train operators to develop their skills. And we can also use IoT to deliver different types of instructions to operator in to different workstations. An idea would be like on-demand instructions where operators can get instructions in the way that they want. In the lab, we have tried digital instructions in different formats. The operators can view our drones into 3D models. There are videos on how operator can assemble the drone, as well as they can look into AR for assembly instructions. This is important because as the complexity increases in assembly processes, we need to simplify the understanding of the assembly procedure. And using these new digital technologies, it makes it a little bit easier for operators to understand how they can assemble different products. The other sources of operational flexibility, such as the systems infrastructure, or machines and equipments and logistics, can be some water. Can also be influenced using Industry 4.0 enabling technologies. These sources are based on how easy it is for the system to be reconfigured, how easy it is for systems to be integrated with the subsystems. For example, how can different workstations can be easily integrated with the main final assembly. How easy it is to integrate that final assembly with the global infrastructures for many global companies, and how easier it is to set up a workstation. So, based on my findings, I proposed use of industrial Internet of Things, as well as collaborative robot applications to influence these sources. We can use IoT as the backbone of the entire system, and having IoT as the backbone can enable us to have modularized production system or manufacturing systems. Having IoT can also help us quickly add and remove workstations from different subsystems. To deliver correct material at correct workstations in fast and efficient manner, we can use different types of AGVs that are integrated with our IoT systems. So we can enable flexible material handling where in the need where a workstation lacks material, or if incorrect material is supplied to workstation, that can be easily replaced. And collaborative robot applications as well. They're quick and easy to set up, and they're quite portable, so we can move around in the assembly or in manufacturing systems quite easily. And I will talk about it a little bit more, but before we go there, I would like to talk to you about these integrated systems and having IoT as a backbone. Also mentioned about these things when we just started talking, when the presentation began. And I would like to highlight it here. So when we talk about having a flexible product and a flexible material handling, so having IoT as a backbone, we can generate 3D assembly instructions right when we design our products. And we have done that with the help of BTC in our lab. During the product design process itself, we can generate the assembly instructions as well as EBOM and bill of materials as well. So the entire system, as it is connected with each other, we can, when it comes to changing products or even changing entire system, we have a clear picture of, okay, we have so many workstations, and we can send these workstations instructions in different ways. And when it comes to changing products, we can use different types of instructions that can be delivered to different workstations. So if we change from, for example, if we change tomorrow from 4-wing drone to 5-wing drone, we can easily generate instructions right while we design the product, and it can be sent directly to the workstation without having to retrain our operators, because they can easily look at instructions into different formats and assemble the products. We can also divide the workload, or divide the assembly process with the different workstations that we have. For example, if we remove a workstation, for example, we have 4 workstations now, and if we remove one, with having a connected system, we can easily redistribute the workload of the workstation that was taken away with the other other remaining 3 workstations having technologies. So we don't have to take the paper and redistribute it again, do the analysis to redistribute the work. So that's an advantage of having a connected system. Now, a little bit about this journey of collaborative robots, collaborative applications, and collaborative robot applications. Sorry, took it in the wrong sequence. We have known collaborative robots for a long time now. They've been around since mid-2000s. We are calling them now as collaborative robot applications, and this was because we have changed the way we look at these machines. Earlier, or even today, we look at collaborative robots as a industrial robot designed to work alongside the human. Now, it's more about the human, robot, and the safety systems. There are external safety systems that are necessary now for a system integrator to certify a working application. But looking forward a little bit, we look at the importance of software as well. And that's why we call it as a collaborative application, because it will have an integrated approach of humans, robots, and safety devices together with the software systems. And it will all look as the same system, not as a robot and machine, robotic as a machine and human as an operator, as 2 separate systems, but everything will be included in the same system. So this is more about pushing to think that robot and machines are the same systems, or the entire workstation should be thought through as the same system and not as separate systems. Looking at the journey that we have had so far, these are the robots that we have, collaborative robots that we have in the lab. And they each come with the different advantages, and they have their own programming systems, different ways to program. Some are still using traditional systems. Some are more influenced by their software than the robot itself. And some are sold as plug-and-play systems. But anyways, why collaborative robot applications? Well, the most advantageous thing about these robots is they are designed to work alongside operators. So you can use them along with operators or as a standalone application. Many robots, they come with pre-programmed templates for common operations such as pick and place or stacking or boxing. So they're comparatively easy to set up, and I compare them with the traditional industrial robots where everything is caged off. Most of them are quite light in weight, and they can be easily moved around. There are robots that can lift up to 35 kilos, classified as collaborative robots, but they are quite huge in size. So I will not say that all robots are quite easy to move around. But the common ones, the ones that are most likely to be applicable or to be applied in your operations, they come as quite light in weight, and so thus they are quite portable. And they can take over easy and unergonomic tasks. They can take over unergonomic works from operators, such as pick and place. So that frees up operator. And remember that the operator is the most flexible resource in final assembly. So if you free up the operator, you already increase the operational flexibility of your system, because the operator can do something else without spending time in doing something unergonomic. Now, coming back to why the system thinking, or why we need to think, why we need to have an integrated approach. So here we have 5 different levels of collaboration. The cell is the traditional caged-off robot. Coexistence is the most common application right now, where the human and robot work alongside each other. Synchronize is where the robot and human work on the same piece, but on a synchronized way. In cooperation, the workspace is shared by both humans and robots, but the task is not performed simultaneously at the same location. So we are not actively working on the same product, but in the full collaboration mode, the robot and the humans are working together on the same workpiece. And when I talked about the need for integrated approach, the need for thinking about the machines, the human operators, the software systems, and as well as the safety systems, is because of this. To achieve a the true level of collaboration, we need to have we need to think about the complexity involved in the processes. So the operator needs to know what the operator is supposed to do while the robot is doing. And to reduce this complexity, we can use different instructions to the operator, so that operator and robot do not cross each other's paths while working on the same workpiece. This is essential when there is quite a big change in products. So as we change, as the product design changes faster, or wide range of variants are introduced in manufacturing systems, the complexity increases, and to reduce that, we need to have an integrated approach where the operator can look into some sort of instructions and not cross the robot's path. Having this systems or the integrated thinking gives you the safety focus approach right from the beginning. So there is no need to look into external safety devices later on, because you're already thinking right from the beginning that, okay, this is the application, this is how we're going to program it, and the safety will be included. And in the end, having all these things gives you competitive advantage. Having the ability for the robot and the human to work together without having to think about safety gives you an advantage to quickly change products and even processes. Now, coming back to our lab, we have used Sawyer to test our collaborative application, and we choose this because it has two inbuilt cameras, one to detect the part and product, and the other, it can monitor the operator. So the robot comes with the pre-built or inbuilt functionality to reduce the process speed when the operator is nearby, and pick it up again when the operator moves away. So the safety feature is already included in the system here. And another advantage of this is it supports lightweight protocols, such connectivity protocols, such as MQTT. So it can be easily integrated with the IoT platform. The test that we did was to have the robot assemble nuts on a wheel hub. So we used the wrist camera to detect where the location of the bolts, and we used a fixture to pick up the nuts and then place it into the bolts. The robot comes with what we call what this company calls them as landmarks. So they can be put anywhere in the assembly or anywhere in the workstation, and once it is programmed, the robot will first start looking for the landmarks, and based on the landmarks, it will calculate where its picking point is, and then take it to the placing point. So it has this inbuilt functionality, which gives us the flexibility of quickly moving it around in the assembly processes. Another example that we have is with our own drones. So we have tested it for quality assurance, and the aim behind this was to see if operator is not available, the robot can take over the task, and how long it will require for to set up and start this process. And so we did this test to see if we can identify or we can do quality checks on the robots. And yeah, we managed to do it in the lab. But we also thought about, okay, if the same things can be, the same system or the same workstation can be also be used for assembly. So we demonstrated that the robot can do quality assurance, but having a gripper attached to it, it can also take over the task of assembling the product itself. There is another example that we did with a battery components. So we used a KUKA as well as UR5 and UR3 to assemble different battery components. But these are not complete collaborative applications. These are collaborative robot applications where we have applied robotic systems to take over unergonomic tasks. But for me, the next step is to develop them into collaborative applications. Yeah, so that was what I had to talk. And
if you have any questions, you can always email us or contact us during either on the website Scilab or directly on LinkedIn or other social medias. And as I said, we will post this to the YouTube channel, so you can look at it again if you want. Do you have any other things to add, Omkar?
No. Yeah, just email or write anywhere on LinkedIn, or yeah, just get in touch if you have any questions or any doubt to look into. Yeah, I will be happy to help and collaborate. Always looking forward to that.
Good. Then we will end this month breakfast seminar. The next one is about automated kitting. So we will have the collaborative applications again, but in the kitting area, more specific. And it will be Patrik Fager who will talk about that then. And there are more information on the website. So good. Have a nice day, everyone.
Yeah. Take care. Bye.
Thank you. Bye.
Bye.